都一个需要看。难道真的要学 Java 吗 ？Kubernetes 还没有玩过 Kubernetes 的，看一下这个 project，好 YouTube，然后看一下 daily life of software developer Kubernetes，我想看一下有没有对 Kubernetes 的职位。
Application and database pods running on it, and the application would still be accessible by the user until these two replicas get recreated, so you can avoid downtime. So to summarize, we have looked at the most used Kubernetes components. We start with the pods and the services in order to communicate between the pods, and the ingress component, which is used to route traffic into the cluster. We've also looked at external configuration using config maps and secrets, and data persistence using volumes. And finally, we've looked at pod blueprints with replicating mechanisms like deployments and stateful sets, where stateful set is used specifically for stateful applications like databases. And yes, there are a lot more components that Kubernetes offers, but these are really the core, the basic ones. Just using these core components, you can actually build pretty powerful Kubernetes clusters.
It's that feeling. The noise fades away and you just fly.
In this video, we're going to talk about basic architecture of Kubernetes. So we're going to look at two types of nodes that Kubernetes operates on. One is master and another one is slave. And we're going to see what is the difference between those and which role each one of them has inside of the cluster. And we're going to go through the basic concepts of how Kubernetes does what it does and how the cluster is self-managed and self-healing and automated, and how you as an operator of the Kubernetes cluster should end up having much less manual effort. And we're going to start with this basic setup of one node with two application pods running on it. So one of the main components of a Kubernetes architecture are its worker servers or nodes. And each node will have multiple application pods with containers running on that node. And the way Kubernetes does it is using three processes that must be installed on every node that are used to schedule and manage those pods. So nodes are the cluster servers that actually do the work. That's why sometimes also called worker nodes. So the first process that needs to run on every node is the container runtime. In my example, I have Docker, but it could be some other technology as well. So because application pods have containers running inside, the container runtime needs to be installed on every node. But the process that actually schedules those pods and the containers then underneath is kubelet, which is a process of Kubernetes itself, unlike container runtime, that has interface with both container runtime and the machine, the node itself. Because at the end of the day, kubelet is responsible for taking that configuration and actually running a pod or starting a pod with a container inside, and then assigning resources from that node to that container, like CPU, RAM, and storage resources. So usually Kubernetes cluster is made up of multiple nodes, which also must have container runtime and kubelet services installed. And you can have hundreds of those worker nodes, which will run other pods and containers and replicas of the existing pods, like my app and database pods in this example. And the way that communication between them works is using services, which is sort of a load balancer that basically catches the request directed to the pod or the application, like database, for example, and then forwards it to the respective pod. And the third process that is responsible for forwarding requests from services to pods is actually kubeproxy, that also must be installed on every node. And kubeproxy has actually intelligent forwarding logic inside that makes sure that the communication also works in a performant way with low overhead. For example, if an application, my app replica, is making a request to the database, instead of service just randomly forwarding the request to any replica, it will actually forward it to the replica that is running on the same node as the pod that initiated the request. Thus, this way avoiding the network overhead of sending the request to another machine. So to summarize, two Kubernetes processes, kubelet and kubeproxy, must be installed on every Kubernetes worker node along with an independent container runtime in order for Kubernetes cluster to function properly. But now the question is, how do you interact with this cluster? Or do you decide on which node a new application pod or database pod should be scheduled? Or if a replica pod dies, what process actually monitors it and then reschedules it or restarts it again? Or when we add another server, how does it join the cluster to become another node and get pods and other components created on it? And the answer is, all of these managing processes are done by master nodes.
If you want to build an app and have no idea how to code or where to start, check out Basic.
Kubernetes，他们说不知道，不知道要不要为什么？说起来都是痛。如果我死了，挺好的。就是所有人都是爱你，不假装所有的灯都是亮的。真是在这这个的类似 KRS。在这像为什么是这样子？这应该更有东西让人筛选，好像不太对耶。要死400多比有些 这是什么？
What is gRPC? When should we use it? Let's take a look. gRPC is an open-source remote procedure call framework created by Google in 2016. It was a rewrite of their internal RPC infrastructure that they used for years. But first, what is an RPC, or a remote procedure call? A local procedure call is a function call within a process to execute some code. A remote procedure call enables one machine to invoke some code on another machine as if it is a local function call from a user's perspective. A gRPC is a popular implementation of RPC. Many organizations have adopted gRPC as a preferred RPC mechanism to connect a large number of microservices running within and across data centers. What makes gRPC so popular? Let's dive a little deeper. First, gRPC has a thriving developer ecosystem. It makes it very easy to develop production quality and type-safe APIs that scale well. The core of this ecosystem is the use of protocol buffers as its data interchange format. Protocol buffers is a language-agnostic and platform-agnostic mechanism for encoding structured data. gRPC uses protocol buffers to encode and send data over the wires by default. While gRPC could support other encoding formats like JSON, protocol buffers provide several advantages that makes it the encoding format of choice for gRPC. Protocol buffers support strongly typed schema definition. The structure of the data over the wire is defined in a protofile. Protocol buffers provide broad tooling support to turn the schema defined in the protofile into data access classes for all popular programming languages. A gRPC service is also defined in a protofile by specifying RPC method parameters and return types. The same tooling is used to generate gRPC client and server code from the protofile. Developers use these generated classes in the client to make RPC calls and in the server to fulfill the RPC requests. By supporting many programming languages, the client and server can independently choose the programming language and ecosystem best suited for their own particular use cases. This is traditionally not the case for most other RPC frameworks. The second reason why gRPC is so popular is because it is high performance out of the box. Two factors contribute to its performance. First is the protocol buffer is very efficient binary encoding format. It is much faster than JSON. Second, gRPC is built on top of HTTP2 to provide a high-performance foundation at scale. The use of HTTP2 brings many benefits. We discussed HTTP2 in an earlier video. Check out the link in the description for more information. gRPC uses HTTP2 streams. It allows multiple streams of messages over a single long-lived TCP connection. This allows the gRPC framework to handle many concurrent RPC calls over a small number of TCP connections between clients and servers. To understand how gRPC works, let's walk through a typical flow from a gRPC client to a gRPC server. In this example, the order service is the gRPC client, and the payment service is the gRPC server. When the order service makes a gRPC call to the payment service, it invokes the client code generated by gRPC tooling at build time. This generated client code is called a client stub. gRPC encodes the data passed to the client stub into protocol buffers and sends it to the low-level transport layer. gRPC sends the data over the network as a stream of HTTP2 data frames. Because of binary encoding and network optimization, gRPC is said to be 5 times faster than JSON. The payment service receives the packets from the network, decodes them, and invokes the server application. The result returned from the server application gets encoded into protocol buffers and sent to the transport layer. The order service receives the packets, decodes them, and sends the result to the client application. As we see from the example above, gRPC is very easy to implement. Now it is so easy. Why do we not see widespread use of gRPC between web clients and web servers? One reason is that gRPC relies on lower-level access to HTTP2 primitives. No browsers currently provide the level of control required over web requests to support a gRPC client. It is possible to make gRPC calls from the browser with the help of a proxy. This technology is called gRPC Web. However, the feature set is not fully compatible with gRPC, and its usage remains low compared to gRPC itself. So where does gRPC shine, and when should we use it? gRPC is the inter-service communication mechanism of choice between microservices in the data centers. Its broad support for many programming languages allows services to choose their own languages and developer ecosystems best suited for their own use cases. We also see increasing use of gRPC in the native mobile clients. Its efficiency and performance makes a lot of sense in the energy and bandwidth-constrained environments that are mobile devices. If you would like to learn more about system design, check out our books and free weekly newsletter. Please subscribe if you learned something new. Thank you so much, and we'll see you next time.
使用 YouTube Premium 享受零广告影片，外加 YouTube Music App， 一个订阅2个 App。When you are building applications with microservices, one of the biggest decisions you'll face is how your services will communicate. That's known as inter-process communication, or IPC. Choosing the right IPC strategy can make your app smoother, faster, and easier to maintain. And there are two main ways your microservices can talk. Synchronous communication is like HTTP-based REST or gRPC, where services expect immediate responses. In asynchronous communication, you use messaging protocols like AMQP or Kafka, where responses aren't immediate, giving you more flexibility. You'll also need to pick the right messaging format, human-readable ones like JSON or XML, or efficient binary formats like Avro or protocol buffers. In this video, I'm not just going to list technologies. Instead, we'll first focus on some crucial design choices. We'll start with interaction styles to clearly understand how your services and clients interact. Then, we'll explore the importance of clearly defining your APIs, especially with an API-first approach. Finally, we'll cover how a client invokes services using messages, look into broker-based and broker-less messaging architectures, and discuss core messaging concepts. Alright, let's jump right in, starting with interaction styles. IPC, or inter-process communication, is basically how your microservices talk to each other. Before jumping straight into the technologies, let's first think clearly about the interaction styles. Why? Because knowing how your services and their clients interact makes choosing the right IPC solution much easier. It helps you focus on what's really important, rather than getting lost in technical details. Plus, as we'll see later, your choice here has a big impact on your app's availability. Now, we can categorize these interactions in two ways: synchronous, asynchronous, one-to-one, and one-to-many. First, think about how many services are involved. In one-to-one interactions, one client talks directly to one service. In one-to-many interactions, one client's request is handled by multiple services. Second, think about timing. In synchronous interactions, the client sends a request and expects a quick reply. It's like a phone call waiting for someone to pick up. In asynchronous interactions, the client sends a request, but it doesn't wait around for an immediate reply, like sending an email and continuing with your day. Let's quickly cover the different one-to-one interactions. In request response, the client sends a request and expects a quick answer. The client might pause, waiting for the response. And this approach tends to tightly couple your services. In asynchronous request response, the client sends a request but doesn't pause its work. It keeps going, knowing the service might take some time to respond. In one-way notifications, the client sends a message to a service but doesn't expect any reply at all. It's purely informational. Now, one thing worth noting. Even if you are using messaging, the interaction can still be synchronous. For example, a service might send a message and still pause, waiting for a reply. Just because you are using messaging doesn't always mean your services are loosely coupled. And we'll revisit this later when we discuss availability. Now, for one-to-many interactions, you typically see pub/sub or publish-subscribe model. Here, the client sends out a notification and any number of services can listen in and react. In publish async responses, the client broadcasts a request and then waits a certain time for multiple responses from interested services. Most real-world apps use a combination of these interaction styles. No matter which IPC style you choose, clearly defining your APIs using an interface definition language or IDL is crucial. This brings us to API first design. In API first design, you first create a clear definition of your APIs. Then, you share these definitions with your client developers. That is the people who will actually use those APIs. You gather their feedback, make adjustments, and only once everyone is happy, you start building your services. And why do you do this? Because it ensures that what you have built actually matches what your clients need. Even in smaller projects, skipping the API first design approach can lead to confusion and frustration. I have seen it happen multiple times. Both backend developers working in, say, Java and front-end engineers using AngularJS confidently say they are done. But then they try running the app and nothing works. It turns out the REST APIs weren't clearly defined beforehand. So even though each side did their part, the pieces couldn't communicate properly. And that's exactly why an API-first approach isn't just nice to have, it's essential. Defining your APIs clearly from the start saves everyone a lot of headaches and keeps the whole team aligned right from day one. Now, let's smoothly shift gears and talk about how exactly you define your APIs. Your API definition will vary depending on the IPC mechanism you are using. For instance, if you are using messaging, your API will mainly involve specifying message channels, message types, and formats. On the other hand, with an HTTP-based API, your definition includes things like URLs, HTTP verbs like get or post, and the formats for requests and responses. At the heart of IPC are messages, and these messages typically carry your data around. This makes choosing your message format a critical decision. Why? Because the format impacts your API's performance, ease of use, and flexibility to evolve over time. No matter which IPC method you are working with, it's essential to pick a message format that works well across different programming languages. You might write your services in Java today, but who knows? You could be using Go, Python, or JavaScript tomorrow. So, you definitely want something language neutral. And a quick tip, don't rely on language-specific serialization, like Java serialization. Broadly speaking, there are two types of message formats you can choose from: text-based and binary. Text-based includes JSON or XML. These are popular because they are easy for humans to read and they are self-describing. For example, a JSON message has clearly named properties, making it easy for services to pick only what they need and ignore the rest. This flexibility means changes to your messages often don't break existing services. To clearly define the structure of these messages, developers use schemas. XML has its XML schema and JSON has the similar standard called JSON schema. And here is why that matters. Schemas don't just document your message structure, they also let you automatically validate incoming messages, ensuring they are exactly what your services are expected to do. Then, we have binary formats like protocol buffers and Avro. These formats aren't human readable like JSON or XML, but they are incredibly efficient. You define your message structure clearly upfront using interface definition language or IDL, and then a compiler generates the code for serialization and deserialization. One huge advantage here is binary formats essentially force you into an API first design, meaning your APIs are clearly defined from the start. Plus, if you are working with strongly typed languages, your compiler will catch mistakes early, ensuring your clients use the API correctly. Now, there is a small difference between these binary formats worth mentioning. Protocol buffers tag each field, letting consumers skip unknown fields easily. On the other hand, Avro requires the consumer to know the schema ahead of the time, making protocol buffers somewhat easier to manage when your API evolves over time. So, choosing the right message format isn't just a technical detail. It directly affects how easy it will be to grow and maintain your APIs down the line. Now that we have looked at message formats, Let's look at a specific IPC mechanism that transports the messages starting with Remote Procedure Invocation or RPI pattern. RPI is a way for services to talk synchronously. Think of it as a phone call between services. One service makes a request and the other answers immediately in real time. Here is how it typically works. Your client service sends a request through something called a proxy interface, basically an adapter that handles the communication details. This proxy forwards the request to a target service, which processes it and then sends back a response through the same proxy, returning the results to your client's logic. It's straightforward and intuitive. And there are multiple ways to implement this pattern, but two of the most popular are REST and gRPC. REST has become hugely popular because it's simple, widely used, and leverages this familiar HTTP protocol. REST APIs treat everything they interact with, like customers, orders, or products, as resources. You manipulate these resources using standard HTTP verbs: get for reading, post for creating, or put for updating, and so on. For example, an order service might have something like this: a post orders for create a new order, and a get orders order ID to retrieve details about a specific order. Now, I've already created multiple videos covering the basics of REST along with some of the best practices to follow. If you want a deeper dive into RESTful APIs, definitely check out those videos. I have linked the playlist for you in the description below. But for a quick refresher, here are some of the main benefits of REST APIs. They are simple and familiar. Most developers already understand them. Easy testing directly from browsers, tools like Postman or command line utilities such as curl. REST naturally fits the request-response communication style. It works well through firewalls and doesn't require extra setup. And there is no need for an intermediate broker, so your architecture stays simpler. And of course, REST isn't perfect. It does have some downsides because it only supports synchronous recursive response interactions. Without an intermediary broker to handle messages, both the client and services need to stay available during the entire interaction, potentially impacting availability. Clients have to know exactly where the service instances are located, requiring you to set up something called as service discovery. Then retrieving multiple resources efficiently in one request can be challenging, and mapping complex business operations into simple HTTP verbs isn't always straightforward. Despite these drawbacks, REST remains the most common standard today. However, there are also some interesting alternatives to REST that you might consider, like GraphQL, which makes data fetching extremely efficient, or gRPC, another robust option for synchronous communication. By the way, if you are curious about GraphQL, I have created a full deep dive video on my channel where I explain everything from scratch. Feel free to check that out too. As we saw, one challenge with REST is that HTTP provides only a limited set of verbs: get, post, put, and so on, making it sometimes tricky to clearly map complex business operations. And that's exactly where gRPC shines. I have also covered gRPC in detail in my previous videos, but let's quickly revisit it next to refresh our memory. gRPC is a robust binary message-based framework designed by Google specifically for building cross-language services and clients. And because it uses a binary message format called protocol buffers in .proto file, it pushes you into adopting an API-first design, something we already discussed as hugely beneficial. With gRPC, you start by clearly defining your APIs using protocol buffers, Google's structured language-neutral mechanism. Once defined, the protocol buffer compiler generates the necessary code, that is client-side stubs and server-side skeletons, for multiple languages like Java, C#, Node.js, and Go. Let me break this down further. The create_order RPC is a unary call, where the client sends a request and gets a single response. It's ideal for operations like placing an order. Track_order uses server streaming, meaning the client sends one request and receives a continuous stream of updates. Perfect for live order status updates like preparing, shipped, or delivered. This example demonstrates gRPC's strength. It supports both standard request response and advanced patterns like streaming, all with strong typing and efficient data transfer. And here is what's great about gRPC. It has high performance. Thanks to HTTP2 and protocol buffers, gRPC is much faster and more compact than REST or JSON. It supports streaming. It enables real-time communications via client-server or bidirectional streaming. It generates reliable client-server code in almost any language and prevents integration bugs and makes API evolution safer and smoother. gRPC, however, doesn't work out of the box in browsers. You'll often need gRPC Web or an API gateway to bridge the gap. And not all firewalls or legacy infrastructure support HTTP2, which could be a blocker in some environments. By the way, I've done a full deep dive video on gRPC on my channel, where I walk through how it works, how to write .proto files, set up your client and server, and how to handle streaming. Check out the link in the description if you want to go deeper into gRPC. You have seen how gRPC gives you powerful features like streaming, strong typing, and high performance, while REST remains a reliable and familiar option. But synchronous communication isn't always the right fit, especially when you need services to work independently without waiting on each other. In the next video, we'll explore asynchronous messaging, how services can communicate by exchanging messages through brokers like RabbitMQ or Kafka, and even through brokerless setups. We'll look at how messaging patterns like publish, subscribe, and message queues help build resilient, decoupled systems. It's a key part for designing scalable microservices, and I will walk you through it step by step. And if you found this video helpful, give it a thumbs up, subscribe for more system design content, and don't forget to check out the description for full gRPC deep dive and REST best practices playlist. See you in the next one.
Thinking about a new career, but unsure where to start? Skip the guesswork with Career Accelerators by Udemy. Step by step, you'll get the skills, hands-on experience, and interview prep you need to launch an in-demand career and adapt to the world of AI. Each Career Accelerator
It's reverse proxy. Proxy and reverse proxy. What's the difference?
Have you ever wondered how some of the largest websites handle millions of users simultaneously without crashing? Or how they transfer your data securely when directing you to the right server? In this video, we're going to dive into the 3 critical web components, which are proxies, reverse proxies, and load balancers. Whether you are an engineer or just curious about how the internet works behind the scenes, in this video, we will break down these complex concepts in simple, easy to understand terms. So let's get started. Imagine you are planning a dinner at a popular restaurant, but you don't want to interact directly with the staff because you're too busy or too lazy or you're shy, whatever the reason. So instead, you have a personal assistant who makes the reservation on your behalf. So the restaurant staff never interacts directly with you. They only communicate with your assistant. In this scenario, you are the laptop that you use to browse the internet, and your personal assistant is a proxy server. And proxy server acts as a middleman between your private network, which your laptop is connected to, and the public internet where your requests go out. And the proxy is protecting your laptop by filtering traffic and blocking any harmful websites or scripts or code before the response gets forwarded back to you. Now, in a company scenario where this is more important, let's say you have many employees and they are browsing the internet and going on who knows what websites. So for example, if your marketing employee visits some shady website and clicks on a link to download some new presentation tool, it may be a malicious website, so they send some virus as a response along with the tool. And when a malicious content or script penetrates your company internal network through one employee's computer, it may do some real damage to many other things in your company. So to protect the internal network, an administrator in the company may configure all internet traffic of all the employees' machines to be routed through a proxy. So proxy will now stand as the guard of your company internal network. You can blacklist any websites that you don't want any of your people to visit, and proxy will block this traffic. But for any other requests that actually do go out to the internet to various websites, it will also scan the responses for any viruses and of course block them if they are malicious. So it acts as a shield between your private network and the public internet. Plus, it can also log user activity to show what sites people are visiting. And on top of that, proxy also has another important feature, which is caching responses. So for example, if one engineer in your company visits this tutorial video about proxies to learn new skills, the proxy will fetch that video from YouTube and cache it locally. So now when 10 other engineers see that and decide they also want to watch such informative tutorial to learn new skills, proxy will just return the cached copy instead of fetching it again from YouTube. And this way it will save bandwidth and reduce any unnecessary traffic to the internet. And this kind of proxy is also called a forward proxy. Now back to our restaurant analogy. Your assistant made the reservation and you arrive.
Yeah, I'm an AI, but I'm here to talk apps. Real apps you can build in minutes with Base 44. This finance app solves your business headaches, tracking invoices, managing clients, keeping payments in check, all in one place. Go to Base 44 and write your prompt, what your app should do, how it should look, and the problems it should solve. Base starts generating your app right in front of you. Invoice list, client profiles, payment tracking. It's like watching a team of developers, designers, and a business coach bring your idea to life. Now let's make it even better by adding features that fit exactly how you work. I'll add scan receipts, digitize them, and act your expenses. Now I can snap a photo and it's logged instantly, no more manual expense entry. Finally, let's add an expenses prediction dashboard that forecasts monthly and yearly costs. Now you've got an app tailored to your business needs, built around the way you work. Start with your idea. Base 44 does the rest.
Now what you do is, instead of wandering around looking for a table yourself, you check in at the reception desk, right? The receptionist tells you, follow me, and shows you to the right table. So here, the receptionist is also a proxy, but this time on a receiving end of the request. It sits in front of the restaurant's internal dining areas, which in our case are the servers, and manages the incoming requests, or the guests, and distributes them to the right tables by checking the capacity and having overview of the entire flow. And this proxy sitting on the server side, handling those incoming requests from clients, is called a reverse proxy. And the function of distributing the guests evenly across dining areas and tables is load balancing, which is one of the key functionalities of a reverse proxy. But it's not the only functionality. Reverse proxies actually have most of the features that the forward proxies have, like acting as a shield to protect the servers. Because when you have hundreds of servers and they all have access to sensitive data or code, it's really dangerous to expose all 100 servers directly to the internet. Instead, you protect them in an internal network and you just put one or few proxy servers as an entry point, and you configure all the security measures on that handful of proxies. So what the reverse proxies will do is they will scan the requests, they will ensure SSL encryption is enabled, so the traffic is encrypted, and will check basically for any security threats or any attempts of hacking into your systems. It also provides caching to speed up responses to the clients and has a logging functionality for doing troubleshooting, for example. So a lot of the features forward proxy has, reverse proxy has as well. And one of the most popular reverse proxies is Nginx, which you may already know as an engineer. If not, I actually have a separate video on Nginx that you can watch here. So as you see, load balancing is just one of the many functionalities of a reverse proxy. So it's a feature that a proxy can perform. Now, many of you may ask here, but what about the cloud load balancers? Why do we need reverse proxy if we have cloud load balancers? Are they a replacement for reverse proxies? Like AWS and other cloud platforms, they all have load balancers. So why do I need an Nginx reverse proxy to load balance the incoming traffic if I can just use AWS Load Balancer? Well, in practice, you actually want to use both. And here is why. For example, you would have your cloud load balancer outside of your servers as an entry point into your private network, while reverse proxy will be routing traffic within your server network. So now you're encapsulating the reverse proxy and those backend servers all into a private network, and the load balancer basically just sits there and does a basic load balancing to the reverse proxy. And this type of layered approach actually makes your infrastructure much more secure and also much more scalable. You may be asking, why do I need to load balance twice on multiple levels? So why do I need proxy inside if I have the load balancing outside? Reverse proxy actually has more intelligent, fine-grained load balancing, which will allow you to do much more intelligent routing to the web servers. So while cloud load balancers distribute traffic based on simple algorithms, like whoever is the least busy, on reverse proxy you can configure more advanced routing logic based on headers, cookies, or session data. For example, you can decide all the requests from the same user, they always go to the same web server. So it will basically check the associated session data or cookies, and it will forward the same client requests to the same server. Reverse proxy can also handle SSL and TLS termination, and it can inspect the encrypted traffic to make more informed load balancing decisions. And this is especially important in microservices architecture, where you may have plenty of microservices, and based on the request path, for example, or the URL, you may want to forward that request to a specific microservice. So it's a very logical load balancing that reverse proxy is doing here. And in our restaurant scenario, this would be equivalent to if our receptionist, for example, knew some loyal guests and showed them to their favorite table to have dinner, or they selected a table with the best view for guests who are celebrating a special occasion, or giving a different menu for vegetarian guests, and so on. So basically more customized request handling based on a little bit more information about the guests. And the setup that I described is actually exactly the one that we would use in a Kubernetes cluster with microservices, where an ingress controller, which is basically reverse proxy for Kubernetes, will handle internal routing and security, while the cloud load balancer will act as the first line of defense, managing the external traffic and kind of shielding them before they get to the cluster. And finally, another question you may be asking here, especially if you are a software engineer, is what about the servers or proxies that start automatically when I run my Node.js or Java application? What are those? Are those reverse proxies as well? How do they run, or how do they start in the background? Well, these are lightweight proxies. For example, Node.js, it doesn't have a built-in reverse proxy, but you can easily create one using its HTTP module or a framework like Express.js, which is actually a framework that most people use with Node.js. So compared to Nginx, for example, which is used in production, Express.js serves different purpose. However, these two can actually be used in combination. So for comparison, Nginx is a high-performance web server and reverse proxy. So it's a technology that can be used for web server as well as reverse proxy. And it's ideal for serving static content, has load balancing functionality. It handles security features like SSL termination and so on. While Express.js is a minimalist web framework for Node.js specifically, used to build dynamic web applications and APIs, and you can actually configure some custom logic and middleware for how the request should be handled for different endpoints. Plus, Nginx also has an advantage that it can handle a large number of concurrent connections very efficiently, while Express.js is less performant in that area. So in proper production setup, Nginx is often deployed in front of an Express.js application as a reverse proxy. So in this setup, Nginx will handle static files, load balance requests, and manage the security, while Express.js will process the more dynamic content. So that's basically the breakdown of proxy versus reverse proxy, as well as load balancer, which is pretty simple if you understand them at this basic level. So I hope I was able to help you understand what these concepts are clearly, and more importantly, how they compare to each other, which I think is probably the most challenging part of understanding proxies and load balancing and so on. Now, if you enjoyed this video and you really want to advance your IT career, then we can absolutely help you with our structured learning programs, which are focused on practical demos that mirror real-life projects. And one of the most important ones that we have is our Certified DevOps Practitioner program. We have trained thousands of engineers who have successfully transitioned from other engineering roles like network engineer, test engineer, software engineer, to getting their first DevOps engineering jobs, transitioning successfully into DevOps, and even sometimes moving countries to work at their dream company. However, there is a prerequisite knowledge required to do this program. This means if you have a solid IT background in any other engineering field, and you know already that DevOps engineering is currently one of the most promising and one of the most future-proof IT jobs that you can have. Our DevOps Bootcamp will literally guide you step by step through every single cloud and DevOps technology that you need to learn and how to combine them and use them together to build end-to-end DevOps processes. If you're interested, you can actually download a free PDF that lists all the real-life demo projects that you're going to be building and learning with throughout the DevOps Bootcamp. And you will find the link to this PDF in the description, along with all the other relevant information for this video. And as always, thank you for watching and see you in the next video.
使用 YouTube Premium 享受零广告影片，还能用 YouTube Music App 听零广告音乐。没错，一个订阅2个 App。设定自动下载，随时随地享受离线和背景播放的观看体验，免费试用1个月。
By the end of this video, you will know not only what Nginx is, but also why it was created and what it's used for with real-life examples.
Real-life examples.
Easy way. First, we will understand what is Nginx actually used for and what are its main use cases to understand why it was created in the first place. Then we'll jump right into the hands-on demo, where we will take a simple Node.js application that just serves an index.html file and start 3 instances of the application as Docker containers on our local computer. And we will actually write the code and all its configuration ourselves. So you aren't just copy pasting some code, but really understanding every step and every single piece of configuration for a proper knowledge, not just shallow surface level knowledge. Then once we have multiple instances of our Dockerized application running, we will install Nginx and configure it as a reverse proxy to load balance requests to our application instances. In this context, we will learn how Nginx configuration works and how to work with Nginx in general. Last but not least, we will configure secure HTTPS connection to our application via Nginx proxy by enabling SSL and configuring Nginx with our self-signed TLS certificate. And in case you've never done something like this before, as I said, I explain everything step by step so you will understand every single detail of the configuration. Now, talking about simplifying complex things. At this point, probably every engineer already has heard of DevOps, which is an exciting but often scary field for many people. And you, as many other engineers, may be convinced already that learning DevOps will make you more valuable and will future-proof your engineering career. However, if you have dived a little bit into DevOps, you probably had a hard time understanding the big picture of DevOps. You probably saw all these technologies that DevOps includes, like containers and Kubernetes, Jenkins, and so on, and the complexity of combining all these technologies. And it makes it very overwhelming and hard for people to learn DevOps without a proper guidance and a roadmap. And that's exactly why back then we created a complete DevOps educational program that fully breaks down this complexity for you, where I literally take you through building the advanced and complex end-to-end DevOps processes. Not just some basic stuff, but actual real-life projects that actual experienced DevOps engineers build at work. And I take you through them step by step with the most understandable explanations without any tech jargon, and actually give you the in-depth, confident DevOps knowledge with no knowledge gaps. As we have done for thousands of engineers already, who many of them we successfully helped make giant leaps in their careers. So if you want to be one of those highly skilled engineers like our DevOps bootcamp students, instead of competing against them in the tech job market, then you can check out all the information about our DevOps bootcamp in the video description. And you can also download the entire roadmap or curriculum for free on the website if you want to familiarize yourself with it first. And with that, let's dive in to teach you how to configure and secure an Nginx reverse proxy for a web application. So let's get started. Back in the day, when the web was still simple with less users, the basic use case was a browser requested a web page from one web server. The web server was a server machine that had a software installed on it that assembled the page and sent it back to the browser, which then displayed it to the user. A piece of software that runs on a server machine and can respond to requests from a browser. And that web server software, that was Nginx. A piece of software that runs on a server machine and can respond to requests from a browser. Then web became popular, so you had thousands or millions of requests per website. Imagine one single server handling millions of requests. That's way over the technical limit of a server software. Well, we need a few more servers to handle that load. So we added 10 Nginx web servers. But now we need something that determines where requests from the browser end. Which one of those 10 servers will handle them? And that's where load balancing comes in. So the same Nginx web server becomes a load balancer that proxies the requests to those 10 web servers. And by the way, the word proxy means to do something on someone else's behalf. So it accepts the browser requests on behalf of the web servers. So it sits at the entry like a concierge and then distributes the load among the web servers. Now, how does it distribute the load? That depends on whichever algorithm was configured on it. It could be a simple logic, such as just whichever server is least busy gets the request, or it could be a round robin, which is a popular algorithm that basically distributes the requests equally in a cyclical manner. So very simple load balancing logic. So now we have Nginx as web server software and the proxy as well. And that load balancing is just one of the functionalities of Nginx proxy. So it's the same server and technology, but with a different task now. So what are those other features or functionalities of a proxy? Imagine New York Times article comes out and millions of people open it on their laptops in the browser. Now imagine every time the request landed with one of the web servers that assembled the response, like put the images together, get them from a database, put text and paragraphs and everything together, edit all the links, sent it back as a response. And this happened a million times. Pretty inefficient, right? Instead, it makes sense to assemble this article, get all the data from a database, put the text and links and everything together once and store it. It's a static article. It's not going to change, right? So just keep one final copy and send it to everyone who requests it. That's caching functionality. And it is another main feature of Nginx proxy server. So you can configure caching on Nginx proxy so you don't have to hit the database or the web servers every time a request comes in. It will just return that cached file. Now imagine we have 100 servers of an online banking application or a social network like Facebook. That makes those servers a pretty juicy target for hackers. They all want to hack into your servers and get the treasure, which is payment data, personal data, passwords, and so on. Now imagine you exposed all 100 servers to public access. So basically all those requests can directly hit each of the web servers. If you do that, you actually make work for hackers so much easier. They would need to find just one issue in one of those 100 servers, and they could potentially break into your entire system. Because all your servers are publicly accessible directly, they can just ping the hell out of them and probe them until they find an issue or an entry because you forgot to update a library or a software package, and they can hack your web server application. So you have to worry about absolutely perfectly securing 100 servers. Now instead, we just give them one server that is the only one that's publicly accessible. You can put all your tightest security efforts on one server instead of 100 servers. And this way, having one entry point, which is the proxy, as publicly accessible entry point reduces the security attack surface tremendously and basically acts like a shield or security layer before all those web servers. So in addition to load balancing and caching, a very, very important functionality of a proxy is an added security for your web servers. Now, talking about security, I mentioned that since we have one entry point, we can focus all our efforts to securing that one proxy server in all aspects. And one important security measure is encrypted communication. So frontend will send encrypted message to the proxy, which means even if an attacker sees that traffic on user's browser or during the transmission, they can't read it. Only the proxy server can decrypt it. But again, for added security, in many systems, proxy that acts as a shield, a security shield, will simply pass on that encrypted message to the web servers, and the web server will decrypt it itself, which is actually a better security practice. So here, the functionality of a proxy is to be able to accept encrypted traffic with SSL encryption. So you can configure your proxy to deny any request that is not encrypted and only accept encrypted requests. Now imagine Netflix, which, by the way, uses Nginx in its backend. And as we know, Netflix has millions of users, so it's getting millions of requests for videos on its web servers. And let's say it's an evening in New York, millions of people come home after work, all at the same time. They switch on Netflix and start watching the most popular series at that time. That means suddenly at the very same time, millions of requests for a high quality video is sent to Netflix. So in this case, imagine that Nginx proxy server would have to send back the entire high quality video to millions of users at once. That's a lot of bandwidth. Imagine how long it would take to send it over the internet cables all the way to the TVs of millions of viewers. That's where compression helps. Nginx proxy can also be configured to compress large images or video files to save bandwidth.
ING, sponsorem głównym jesiennej trasy braci Kacperczyk. Doświadcz wyjątkowych emocji i...
So it became very popular in containers as well and made its way as one of the most popular solutions for Kubernetes ingress controller functionality. Ingress controller is essentially a proxy with advanced load balancing functionality, but for Kubernetes. So what Nginx was doing for simple web servers, it's now doing for Kubernetes cluster in the form of ingress controller, acting as a proxy and load balancer that receives the incoming traffic first, and then based on the configuration that we define, forwards it to the right service inside the cluster. Now, this load balancing configuration, as well as the logic, is more advanced and more Kubernetes specific, but the idea is pretty much the same. And I actually have full videos on ingress and ingress controller and how to configure it, you can watch on my channel. In fact, I create these tutorials regularly on a lot of interesting technologies. So if you want to educate yourself in tech, make sure to subscribe and activate notification to get those new tutorial videos. Now, there are actually many ingress controller implementations out there for Kubernetes, but Nginx is one of the most popular ones. And I have actually used Nginx ingress controller in most of my projects as well. Now, some of you may be thinking, doesn't each cloud platform have its own load balancer? Why do I need Nginx as a load balancer? Well, you actually need both. Nginx ingress controller, which acts as a load balancer, is used inside the cluster. So unlike the proxy for web servers, it's not publicly accessible, so you can't access the Nginx ingress controller directly from the browser. It actually lives inside the cluster network and forwards the requests internally. So who is getting the requests from public? What is the public entry point for the browser requests? That's the cloud load balancer, like AWS ELB, for example, which then forwards that request to the ingress controller inside the cluster. And this is important because it adds a very important security layer to those requests. So the cluster component is never directly exposed to public access. Instead, every request comes from the cloud load balancer, which then forwards it to the ingress controller within the cluster, which then routes the traffic based on intelligent logic to different applications within the cluster. And with intelligent routing, what I mean is if you have one large application with lots of sub-segments or microservices, for example, you can configure your ingress controller so if the request URL includes online cart, it routes the traffic to online cart microservice. If it includes payment, it routes the traffic to payment service, and so on. Now, as I said, ingress controller in Kubernetes environment is a bit more complex setup than web server environments with proxies. But since Kubernetes became so popular, you kind of can't really avoid it. But I know many engineers, especially software engineers, don't really like dealing with all the Kubernetes configuration files and dealing with Helm charts, etc. to install various services they need in the cluster. And that's where an abstraction of that complexity can be a great solution for engineers. And this is exactly what Pulumi, the sponsor of this Nginx crash course, actually offers. They have created a solution to allow engineers to use whatever programming language they are familiar with to provision and configure resources in Kubernetes. So you could set up and configure the whole ingress control configuration, for example, in the Kubernetes cluster without ever interacting with the underlying Kubernetes components, which I know a lot of engineers will be happy about, simply using your preferred programming language as an abstraction with Pulumi. So Pulumi hides all that complexity for you, which you can imagine makes engineers much more productive. So huge thanks to Pulumi for sponsoring us so we could create this valuable crash course for you.
If you want to build an app and have no idea how to code or where to start, check out Base44. I built this daily habit tracker that helps users log small wins, track their mood, reflect on past entries, and see how far they've come. It's fully functional, and I didn't write a single line of code. You start by describing your idea, what you want it to do, the features, the look and feel. Now watch Base do its magic, designing the interface, building the database, wiring the logic. It's like asking a team of engineers, designers, and product managers to create your vision instantly. Once you have your first version, you just keep going. I add dark mode, polish the transitions, and make sure it works smoothly across devices. The best part? I can just stay in flow. No blockers, no switching tools, just building. So start with your idea. Base44 does the rest.
使用 YouTube Premium 享受零广告影片，外加 YouTube Music App， 一个订阅2个 App， 免费试用1个月。
Now, some of you who've been in IT for a little longer may have worked with Apache Web Server. So what's the difference between Apache Web Server and Nginx Web Server? Well, not much actually. Nginx and Apache Web Servers do pretty much the same thing. Just like Nginx, Apache also used to be a basic web server, and then they extended its functionality as a proxy. And it has all these benefits and functionalities of a proxy that we discussed. Apache was actually already widely used when Nginx was created. And the major benefit of Nginx was that it was faster, more lightweight, and definitely had an advantage when it came to serving huge amounts of static files. Plus, as you saw, it has a pretty easy configuration as well. And Nginx also became more popular in the container world. So let's dive into our demo project. And we are starting with a very simple application, and we're going to build this up step by step. We have one static index.html file, which basically displays an example website with some sections in it, and it references a few images. So we have something pretty to look at on the UI, and those images are also in the project. So super simple. So let's actually open this index.html file and see how it looks like in the browser. And I'm in the Visual Studio Code, and here I can just click reveal in Finder, and if I double click or just paste in the absolute path of the index.html file and hit enter, that's our website. Those are the images that are being referenced. Obviously, it looks ugly, but we have something in the UI to display. And all this is static because, as I said, we just have one simple index.html. And as you see, this is just served statically from the file location. That's it. That's what we are starting with. So now, as the first step, let's actually add a backend server to serve this index.html file to the browser instead of us having to open this like a static file, basically, like this. So that's also very simple. We're going to use Node.js and create a very simple server.js. And I'm going to paste in the Node.js code with a very simple logic. It basically starts a backend server on whatever port we define here. So on port 3000, it's going to start a server using Express.js module, which is basically a lightweight server module. And once the application starts, it will serve the index.html to the browser using this logic. So every time we access the application on this root path, basically, it's going to send back the index.html file. Very simple. And it's just going to log out in the console here that the request has been served or replied to by the Node app. And we're also serving the images because this index.html references the images, so they also need to be sent to the browser or served just like the index.html file. So all these files, basically all these static files, are served from the backend server to the browser. That's what's happening here. Super simple. And as you see, we have two packages that we are using here. And that means we need to actually download those packages from internet to our local machine so we can start this application. And for that, I'm going to create a package.json file. And I'm going to paste it in as well. And you have all these metadata, like name, version, description. And these are the dependencies, those two packages that we need for the application. And now, in order to execute our application, we need Node.js installed locally, so we can execute this. And in order to download those packages, we need npm, which is Node's package manager tool. We can install both of them simply by installing Node, which is very easy. If we look for Node.js download, you can execute those commands, or you can even download a pre-built installer, again, for your operating system. I'm actually going to download this one to show how easy it is. Just double click. Install. And now you should have Node available. There you go. So Node also installs npm, which is Node's package manager tool for downloading those dependencies that we define in package.json, managing those dependencies, and so on. So the first command is going to be npm install to install those two packages that we defined here. And there you go. Those packages have been downloaded. So now that we have installed those packages, we can execute node server.js, which will basically start this application and print out node app is listening on port 3000. And now it waits for our request to serve index.html, which means if we go back to the browser, and now I'm going to do localhost 3000, that's the port that we defined here, we should see our page served by Node.js backend. And as you see, difference here, this is directly from the file, and this is from localhost. And whenever we refresh a page or visit a page, this logic gets executed, and you see that request served line is printed out in the console. Awesome. So this is just very super simple setup. Now we're gonna Dockerize this application and then put Nginx proxy in front of our Node.js application.
堂堂天下无双的将军，到底怎么会变成今天这样？
师兄啊，这月朗红绳竟是1号。
保险起见，烧，全烧了。
我是保人姻缘的妖，但其实又对此一无所知。
唐丫头，怎么管起人类的事了？你不是只给妖怪医病吗？
说对了，我正要出门看诊呢。
此妖可是上了雷神黑名册，今日必要带归天界。
此妖是我的病人，还请卖个面子。
GoDaddy has the perfect hosting plan for any website, from low-cost shared hosting to your own virtual server. Every plan comes with a 99.9% uptime guarantee, along with a free domain name and award-winning support. No wonder we're the world's #1 web host. Unlock your online potential today with GoDaddy.
So instead of the browser request going directly to the Express server on Node.js, it will first hit the Nginx server, and Nginx will then forward the request to Node.js. So let's stop our application. And as a first step, we're going to Dockerize our application, and we're going to start 3 instances of the same app. And if you don't know Docker or how to Dockerize application, it's actually very simple. I have a separate Docker crash course, and you can learn step by step in detail over there. So what we need to do to Dockerize an application is obviously a Docker file. And as the rest of our application code, this is also going to be very simple Dockerfile logic. And let's go through them one by one. We are basically using a Node image because it's a Node application, so it needs to have Node and NPM available, just like we installed it on our local computer. The Docker container that starts this application should have Node and NPM. Then we basically create this /app folder and define it as a work directory, and then we copy these local files from our project into this folder inside the Docker container. And we basically copy the server.js because that's the backend logic that needs to be executed. Then we copy the index.html file into that work directory. We then copy images, the entire image folder, basically inside /app/images folder, because that's where index.html expects them to be. And then we also copy the package.json because that's where the dependencies are defined. Then we execute npm install to download those dependencies. We expose port 3000 inside the container. That's where our application will be accessible. And then we simply do the same as locally, just start the application by executing node server.js command. Super simple. And with this Docker file, we're going to now build our Docker image. And again, I'm going to need to start my Docker application. And once Docker is up and running, I can build an image based on this Docker file. So Docker build, let's call our image my app. 1.0 and location of the Docker file, which is the current directory, and let's execute. And there you go. Our image was built, and you can also check that right here, or with Docker images. There you go. So we have an image of our application that we can start multiple copies of, or multiple containers from, which is what we're going to do. So we just built the image, but the application is not running as a container. So let's actually check that. So if I refresh, the site is not accessible because our Node app is not running locally. So we can start it now as a container instead of executing Node server.js on our computer. So I'm going to do docker run, and let's actually bind the port 3000 to 3000 inside container. And this is the image that we want to build the container from. Let's run. There you go, app listening on port 3000. And if I refresh, we have our application accessible again. Awesome. So now, if I refresh, we have our application accessible again. Awesome. So now, this is our container, and I'm going to stop it because, as I said, we want to start 3 instances of the same application instead of just having one. So again, nothing running. And in order to start multiple instances or multiple containers, we're going to use Docker Compose. So let's clean up all this, and I'm going to create docker compose.yaml file. And I'm going to, again, paste the code, which is also a very simple configuration. So let's go through it. So we have 3 services defined here, and we call it app1, app2, app3. And this is going to be the same application in all 3 cases built from the same Docker file. So with Docker Compose, you can not only start existing images, but you can actually build an image from a project or from Docker file and then start those newly built images. So that's what we're doing here. We're building the image of app1 and we're starting it. We're building the same image of app2 and app3. And what we're doing is to differentiate between those replicas of the same application. We're just gonna pass this environment variable that basically says this is app1 or replica 1 of the application, this is replica 2, this is replica 3. And we can use this environment variable inside the application itself. So what we're going to do here is a very simple change. So basically, we're passing this environment variable to our application inside that Docker image that we're building. So this application will have access to this environment variable inside the logic. And we can access environment variables in Node.js using process.env. And whatever the name of the environment variable, which is app name. And this is going to be, I can save it, let's see, a replica app or something like this. So instead of node app, we can say, and again, this is Node.js syntax. And we're going to do string concatenation. So basically, we are saying this request is served by whichever application replica that is. And we're going to do the same right here. So in the logs, we will see which of the 3 replicas the request is handled by. So the application will run fine without this change, but we're just doing that as additional information for us in the logs to see and to compare which application replica is currently serving the request. Awesome. So that's prepared. And now when Docker Compose builds this application, it will grab the Docker file and it will basically copy all these files, including server.js, where we made those changes, and it will build a new image which contains this changed logic. And as we see here, it will read the value of the app name environment variable for each instance. So for this service, it's going to use app1 here. For app2 service, it's going to use app2 here, and so on. And then we have final configuration, which is port. And since we want to run all 3 replicas on the same machine, on our local host, the ports need to be different because we cannot run 2 applications on the same port, right? On the second time, it's going to say error, the port already in use. You can't do that. So the application inside the container itself is going to start on port 3000. That's what we're also defining here.
It's that feeling.
3000
The noise fades away and you just fly.
And in Dockerfile as well. So this will stay the same, but on the local host, we're then binding that on port 3001, 2, and 3. That's how it's going to work. So again, this will start those 3 services with these 3 slightly different configurations. And now all we need to do is start Docker Compose to create and start those 3 Docker containers. And we can do that simply by executing Docker Compose up build, and we're going to start all the containers in the background. Let's hit enter. And there you go. Let's see the logs. As you see, it built the Docker images for app 1, app 2, app 3, and then it started 3 containers in the background, which means if we do Docker PS, we should have 3 containers all running the same application, but on 3 different ports, which means those 3 ports, 3001, 2, and 3, obviously nothing is running on 3000, but if we check 3001, there is our replica number 1. This is, we check 3001. There is our replica number 1. This is replica number 2. And then we have replica number 3 as well. And we can check the logs. And this is application 2. And we see request served by app 2. And same with the other ones. This is number 3 and so on. Awesome. So now the final part that is missing is we don't want to have to access each replica separately one by one. We want to have one entry point that then automatically forwards the requests to one of those 3 replicas. And that entry point is going to be Nginx. So we're going to now install and configure Nginx proxy and put it in front of those 3 application instances to load balance requests to them. Plus, we also want to configure a secure connection to our application. So instead of HTTP access that we're using right now, we want to be able to access our application using HTTPS endpoint, which we will also configure on Nginx. So Nginx basically will act as a load balancer and as a proxy that secures the access and does all sorts of other configuration before the request even reaches the backend server. And in order to configure Nginx, obviously we need to install Nginx locally first, which is also pretty simple. On macOS, it's simply brew install Nginx. Let's execute.
Nginx, yeah. So, just the cheese, each one is the largest of the character, the first one, the strategy, nothing more than the same. More than the same. We can choose the sense of harmony from the conscious and the twist. We can resolve and trace it. This is the machine. This is the just like a penguin in yourself. And also this cost is the cost of uncommon cultures. The conflict is connections is not about the peace versus future. People prefer relations. 一直真的会支持了是有关这个东西。但是有那个比如说你要跟你这个是其他的同学就是不要说是按照学校的就是口不好意思，是的。